Welcome to the next lecture on this series of lectures on purification and separation methodologies. In today's lecture, we will continue our discussion on column efficiency. Thereafter, we will build up this concept using a concept of plate theory, and further we will describe the asymmetry in chromatographic peaks. And towards the end of this lecture, we will describe a new term, peak capacity. So, let us begin. This is what we saw in the last lecture. Our elution chromatographic peak ideally should appear as a square peak, which never happens. And what happens normally is this Gaussian curve as a chromatographic eluted peak. Now, what has basically happened in this is the peak has broadened, and this peak broadening is related to column efficiency, and this is something we are going to look into in today's lecture in more details. Now, column efficiency is inversely related to the rate of peak broadening per unit time. This is evident from these two images here. Now, the image on the left hand side shows two peaks with more peak broadening. It means the W in these two is more than the W in these two peaks which are on the right side. Hence, it is obvious we could see in the first case the column efficiency is low in comparison to the second image, where column efficiency is high. Hence, what can be inferred is lesser is the peak broadening, higher is the column efficiency, and better is your column, or better is that separation experiment. That is one thing. This concept of column efficiency can be dwelled upon using a couple of theories. First being plate theory, a very prominent theory proposed by Martin and Singe in 1941, for which they received a Nobel Prize later. And the second theory is a rate theory, which was proposed by another eminent scientist, Van Demeter, in 1956. This Martin and Singe theory is old, whereas this Demeter is comparatively a recent theory to explain column efficiency. We will start to understand this plate theory and dwell upon how this is related with column efficiency. What plate theory basically says? Now, here is your column, right, of a length L. Now, to understand this plate theory, we need to visualize this column of length L into some very small minor segments which are shown here as bars, and each one segment is called a theoretical plate. It is hard to visualize, right, because this is a conceptual imaginative concept. There are no such theoretical plates physically present in this column. The column is a uniform surface coated with the stationary phase. Now, to understand this, I would like to draw an analogy. Let us say you are staying in a room and you have to now from one corner of the room to travel to the next corner of the room, and every step which is taken can be construed as one physical barrier, right. So, one step taken forward means you have crossed one barrier, another step taken means you have now shifted that barrier to one step ahead, right. This is just an imaginary barrier, there are no barriers existing, right. Likewise, in the column there are no such physical barriers, but what we are trying to say is that this segment, this length is imaginary, is conceptually consist of n number of such barriers, n number of such segments. Now, what I do here? Let me zoom into one such segment, any of these segments, and I bring in here. Now, what do I see in any of such segments? I notice that in each segment your solute is trying to align and distribute or partition itself between stationary phase and mobile phase. These blue dots signify the solute particles. Hence, as you could notice, this solute particle here is in equilibrium and has partitioned itself into stationary phase and mobile phase. The real equilibrium would not establish, but then it tries to attain an equilibrium. The same thing happens in the next step and the following step. For example, now you have these many particles of the mobile phase which will then interact with the next segment, and in that next segment it will again partition between stationary phase and the mobile phase, right, and the process will continue. Hence, this theoretical plate N is the one functional unit of a column, be it any kind of column, right. So, a column consists of n theoretical plates. What else we get? So, as I said, in this theory the Nobel Prize was awarded in 1952 to Martin and Singe. Now, let us try to look at it a little bit further. As I just stated, so once introduced into the chromatographic column, the solute would begin to distribute itself between stationary and mobile phase in accordance with its partition coefficient, which is denoted by K. Now, that is a new term, we have not seen it so far. What is K? This K partition coefficient is mathematically equals to concentration of solute in the stationary phase, which is Cs, upon concentration of solute in the mobile phase, which is Cm. So, at each plate, theoretical plate, there is this K which is established, right, and the value of K, as obvious, can stay between 0 and 1. If the value is 1, it means the concentration of solute in both the phases is just equal, right. Now, for example, the value of K, if it is 0.4 in this case, what would that mean? That would mean 40% of the solute particles have partitioned themselves into the stationary phase. Now, this is the same thing I was talking about in the previous slide. Let me explain it once again. Let us assume you had 10 solute particles in the beginning, all right. So, as soon as your solute reaches first theoretical plate, 4 of those particles would move into stationary phase and the remaining 6 will enter into the mobile phase, and that mobile phase with 6 solute particles will enter the next theoretical plate. In the next theoretical plate, out of those 6, again 40% would go to the stationary phase and the remaining 60% will go to the to this mobile phase. By then, these 40 or 4 molecules, 40% of the solutes which were remaining in the first stationary phase, first theoretical plate, have again aligned themselves, and 40% out of those 4 molecules have now stayed back in that theoretical plate and rest have gone to the mobile phase. So, it is a dynamic stage. At every theoretical plate you would have 40% of the solute particles going into stationary phase and the remaining 60% would be going into mobile phase, and that process would continue. So, slowly your solute particle is reacting, interacting with the stationary phase, getting partitioned and slowly coming out. This is the basis of chromatography. This is the basis of separation, as we were seeing in the previous lectures, right. Now, this should not confuse you, as I am talking about partition coefficient and I am denoting it with capital K here. In the last lecture, we discussed about capacity factor, which was denoted by small k. So, it becomes important for us to realize whether these two are related in some way, right, and how these are different. So, this capacity factor we saw in the last lecture equals to Tr minus Tm upon Tm. This can be expressed in terms of moles also, but in terms of time, this capacity factor tells you about the time spent by solute in the stationary phase upon time spent by solute in the mobile phase. Now, if you convert this thing into moles of the solute, it can easily be converted into this equation. So, this K would be equal to Cs Vs upon Cm Vm, whereas Cs and Cm it is the concentration of solute in the stationary phase and mobile phase, and likewise Vs and Vm would represent volume of the solute in stationary and mobile phase respectively. Now, in this equation, this Cs upon Cm is nothing but capital K, which is partition coefficient. Hence, this capacity factor K equals partition coefficient times Vs upon Vm. Therefore, this capacity factor is directly proportional to partition coefficient. So, more is partition coefficient, more is the capacity factor and more is the retention time. All are now getting related, and we are just trying to now fit in some pieces of the puzzle here. So, the significance I talked about in the last slide, let us look at it from another perspective here. It is this yellow solute which contains, let us say, two components. One is this red component and another is this white component, and you load it in a column, right, and a mobile phase will start to carry this forward. Now, at every step these arrows represents plates. So, at every step these theoretical plates, every theoretical plate will interact with this red particle and this white particle. Now, what happens? Let us say this red particle is one which is having high K value, that is high partition coefficient value, right, and this white is the one which is having low partition coefficient value. As the time progresses, as it starts interacting with this second plate, then third, then fourth, then fifth, gradually because of their difference in partition coefficients, this white will start to move further in comparison to red, and that is how the separation would be achieved using this concept of partition coefficient. This is the physical basis of their separation in chromatography. So, that is the significance here. Let us now try to relate plate theory with column efficiency. We just got this concept of N and this number of plates and theoretical plates. How these are related to column efficiency? Let us try to see. Now, let us assume that you have a perfect Gaussian profile for a chromatographic peak, which we have also seen in the last lecture as well, right, in which we define terms like Tm and then Tr, which is retention time, and then W, which is the width of the peak. There is one more term which I like to define here this time, and this term is W 1 by 2, which is peak width at half the height. It is important for some equations which are coming up now, in which we relate this plate theory with column efficiency. Let us see how. So, this column efficiency in terms of theoretical plates N can be shown as n would be equal to 5.54 times Tr upon W1 by 2 whole square, right, and this W1 by 2 is the same thing which I defined in the last slide. Its peak width at half the height. This also equals to 16 times Tr upon W whole square. So, this can be related, n, which is number of theoretical plates, can be related to half peak width or it can be related to peak width, and that certainly has a relationship with Tr. So, what do we make out of it? Now, in this equation, let us try to get significance of this equation. Let us now imagine that W1 by 2 for two peaks which are eluted out is constant. In that case, and this is the chromatogram, you could see this is one peak here and this is second peak here, and let us assume that W1 by 2 is the same for both. What is different? The difference exists in retention time. The one peak with large retention time Tr will have large theoretical plate number, right. So, you could see a chromatogram, and in a chromatogram if you see a peak which is having higher retention time, you could say that for this peak theoretical plate number is more. And if this is the case, then you could easily say that column efficiency vis-a-vis that particular peak is high. Now, once I say that, I must also put a rider, and the rider is you cannot infinitely change the plate number, it cannot have any infinite value, right. There has to have some constraint, and those constraints we will see in times to come. But for the time being, I want all of you to remember that for gas chromatographic, generally this peak plate number stays at 600 per meter, whereas for HPLC this number can go up to 40,000 to 70,000 per meter. In general, for a good column, we always believe that a number, somewhere close to 10,000 is good enough if you want a good column efficiency. So, a plate number of 10,000, right. Now, look at it from the perspective of peak width. Now, in this case, I will keep Tr constant for two peaks. Let me see what happens. So, in this image, as you would notice, Tr for this peak and Tr for this peak is exactly the same. What is different? The difference exists in peak width. In this particular case, peak width is more, and hence if peak width is more, its theoretical plate number n is got to be small. And for the other case, when peak width is small, your theoretical plate number is got to be large, and hence larger the plate number, higher is your column efficiency. So, what as a chromatographer you are looking at? You are looking at peak width which is small and Tr which is high if you want a good column efficiency for your chromatographic separation. This is the significance of plate theory. At this point, it is important for us to also describe asymmetric peaks and see how they are different from the normal Gaussian peaks. Now, ideally what happens, a chromatographic peak should be symmetric about its center and should follow a Gaussian distribution, as you could see in this image here. How would you note that your peak is symmetric? Now, it is easy. You just draw a vertical line from the apex of your peak, and this apex should now split up the peak width into two equal halves. What I am saying is here is that this AB should be equal to BC. If that happens, your peak is symmetric. But what happens in several cases that once you note this AB and measure it up, you realize this AB is not equal to BC, and all such peaks where this AB is not equal to BC, we call those peaks asymmetric peaks. This measurement generally is carried at 10% of the peak height. What it means? Let us say this is your overall peak height. So, 10% from the baseline you measure this AB and BC, and that tells you about the peak asymmetry. Now, there is something AS, a term AS, which actually measure up the content or the level of peak asymmetry, and this AS is equal to distance from the central line of the peak to the back slope, which is BC, upon distance from the center line of the peak to the front slope, which is AB. So, this BC upon AB gives you a measurement of peak asymmetry. If this value is 1, certainly your peak is symmetric. If it changes from 1, then your peaks are asymmetric. There are two types of asymmetries. In one case, this AS would be greater than 1, which means BC, this component BC is higher than AB, and if that happens, we call this phenomena tailing, okay, tailing of peaks. In another case, if AS is less than 1, it means AB component is more than BC here, we call this phenomena fronting, right, and both fronting and tailing are asymmetries. Let us try to see this a little bit more further. Now, for an ideal Gaussian peak, as I told you, this AS should be equal to 1. Now, what it means? AS1 means that partition coefficient is constant for all concentration of the solute in all theoretical plates. If that happens, your peak would remain symmetric. It means at all theoretical plates, let us say that 40% which we saw in the last slide, in every theoretical plate only 40% of the solute will remain in the stationary phase and 60% will remain in the mobile phase. If this is constantly and uniformly followed all across the column in all the theoretical plates, your peak would always come out as a symmetric Gaussian peak having AS equals to 1. If this is the case, then K, as you know, equals to CS Cm, which would mean that CS would be linearly related to Cm. Now, what that means, if you draw a graph of CS as a function of Cm, it should provide you a straight line. This is what should happen in a symmetric peak. So, certainly it would not happen in an asymmetric peak, right. So, what happens in an asymmetric peak? With a peak having fronting. Now, for a peak having fronting, if you draw the same graph between CS and Cm, you would notice that after some time this linearity is distracted and it goes off towards this CS side. What that means? That means that beyond a point, more of your solute remains in your mobile phase than in stationary phase, which means that this 40% which I was talking about in the previous slides gets distorted and disturbed, and beyond a point you realize that, let us say, in nth number of theoretical plate, it is just 20% which is staying in the stationary phase and 80% is staying in a mobile phase. Why should it happen? It should only happen if your stationary phase and the sites of the stationary phase on which solute would interact have become clogged, and they would become clogged when your sample is of very high concentration. And to have a solution for this, one just needs to dilute the concentration of a solute, and this problem should wean off. It is more simple in comparison to peak tailing. What happens in peak tailing now? If you draw a similar graph, now in that case again that linearity should be distorted, but it should be distorted towards this Cm side. What it means? That beyond a point you should have more of your solute in the stationary side rather than in the mobile phase. Now, again coming back to the same 40% that example I am picking up. So, beyond a point, let us say in that nth theoretical plate, it is not 40%, but 60% of your solute is now residing in the stationary phase, and it is just 40% which has now transferred to the mobile phase. Why should it happen? It should happen only if some sites in your stationary phase are acting as highly active sites. In other words, it should happen when there are more than one retention mechanism present in separation. Confused? Let me explain it. Now, in this slide, I am going to explain peak tailing and I am going to pick reverse phase column, which is a C18 column, right? In C18 column, the interaction of a solute with a stationary phase is purely hydrophobic. Remember, we discussed this in the last lecture. Now, despite having this major retention mechanism through hydrophobic interactions, there are still around 50% of the sites of the stationary phase which are still not covered by C18 groups, which means they are still very polar, where this hydrophobic retention mechanism will not apply. So, what would happen to those 50%, the remaining 50% sites of the stationary phase? This is what would happen to those sites. Let us imagine your solute particle contains some polar groups, for example, amine here, right. So, this amine, instead of and also along with undergoing hydrophobic interactions with C18 phase, it would indulge in hydrogen bonding with this OH remaining 50% of these OH sites, which means that once it is retained, it will be very difficult for this solute particle to get retained. It will be rather sticking to this column, and hence you would observe this phenomena of tailing. So, what are the solutions? What should we do? The solutions are two-phase. First thing is, you can rectify your stationary phase. For example, in this case, a column pretreatment should seal these naked OH groups and should provide associated silanols. And now, in this case, there is nothing with which those polar amines could react or could interact, right. So, then your tailing should be rectified. Another way of rectifying this peak tailing is, you could modulate your mobile phase. How one can modulate a mobile phase? Let me explain. So, in this case, the solution contains your solute, which is your mobile phase. Your mobile phase contains the solute, and it also contains, let us say, for example, triethylamine, just 1 or 2% of triethylamine. This 1 or 2% of triethylamine is sufficient enough to plug in, engage these active OH groups, which are in addition to those C18 groups. Hence, your solute will only engage in hydrophobic interactions, and there are no other mechanisms, no other interactions which are going on, and hence the tailing should be circumvented. So, these are the two ways of controlling tailing, and this is about the asymmetry in peaks. With this, I come down to the last topic of this discussion, which is peak capacity, and this is denoted by Nc. Now, generally for solutes which contain many components, it is not just 2 or 3 components, several components. For such solutes, relative performance of column efficiency is given by peak capacity rather than theoretical plates. And this peak capacity defines the maximum number of components of solute which can be resolved on a particular column. Let us try to understand this. Now, I take an example of an isocratic separation, isocratic mobile phase, and you know an isocratic mobile phase is one where the composition of the mobile phase remains constant throughout the elution. So, for an isocratic separation, this Nc equals to 1 plus square root of n upon 4 times natural log V max upon V minimum. This V max upon V minimum are the minimum and maximum volume of mobile phase in which your solute can be eluted. Try to understand it. Let me just explain it a little bit more and hope you would understand this concept. Now, as you would see in this equation, your Nc, which is peak capacity, is directly related to theoretical plates. So, in a column, if there are more theoretical plates, this peak capacity would be more, and hence we can infer that this particular column is more likely to separate complex mixtures. Likewise, if V max is far greater than V minimum, it means this factor, natural log factor, is high, which means peak capacity is high, and that again means the same, that your column is more likely to separate complex mixture. Now, what does it mean? It means that, for example, for an average of 10,000 theoretical plates, you could devise a column having 10,000 theoretical plates, and let us say in that column your first component out of your solutes comes at 10 ml, whereas the last component of your solute comes at 500 ml once 500 ml of solvent has passed, which means this factor V max upon V minimum turns out to be 50, right, 500 upon 10, which comes out to be 50, and this square root of n is 10,000, this n is 10,000. If you solve this equation, your NC comes out to be approximately 100, which means for such a column you could have a mixture of around 100 components which can be separated in one single chromatographic elution. Now, having said that, I must also reiterate that this theoretical number of NC is generally less than the actual number of NC which is experienced experimentally. Nevertheless, you could get at least some idea about how many components which can be resolved using this peak capacity factor. I hope you understood the concepts discussed in today's lecture. What we are hoping of in the next lecture is we will dwell upon the rate theory, and we would use Van-Demeter equation to build up the concept, and then finally we will try to see how we should optimize chromatographic separation for using various factors as resolutions, as plate height, as capacity factor, how we could have an interplay of all these factors which we have learned so far to get a separation which is excellent, right. So, I hope to see you in the next lecture. Thank you very much.